Hi, welcome to Office Hours. My name is Patrick Curran, and along with Dan Bauer, we make up Curran-Bauer Analytics. In this episode, I would like to talk about how can we expand our growth curve model, whether it be estimated within the structural equation modeling framework or within the multi-level modeling framework. How do we expand a growth model to incorporate predictor variables that themselves change over time? So in a prior video, I talked about incorporating what were called time-invariant covariates. And all that means is it's a predictor variable that the numerical value that it obtains is independent of time. So we might have biological sex, we might have country of origin, we might have birth order, any of a number of characteristics of the individual that are stable and therefore are invariant to the passage of time. And as we talked about in that prior video, I'll do kind of an accelerated path diagram is if we had, say, antisocial behavior, that was the example we were using, and we had some intercept and factor, and we had some slope factor that related to the repeated measures, is we could bring in a covariate, say biological sex, that predicted the intercept, predicted the slope, gamma 1 and gamma 2. And what that implied was that instead of having just a single trajectory of antisocial behavior, there was one trajectory that on average held for girls and one that on average held for boys. And the difference between the intercepts were gamma 1, because this is a gamma unit shift in the intercept as a function of a 1 unit shift in the predictor. Well, a 1 unit shift is moving from girls to boys. Same holds in the increment in the slope, and so the difference in the slopes is gamma 2. And what we found was that we could incorporate one or more covariates. Here's a binary, but I talked about how we would include a continuous predictor as well, that shift the conditional means of the intercept and the slope to provide different conditional trajectories at unique values of the predictors. This all works exceedingly well, both in SEM and multi-level, as long as the predictors themselves are not varying as a function of time. But what if we have a predictor, one or more predictors, that we'd like to incorporate into the model that themselves change over time, that the predictor can have repeated measures as well? That we're going to refer to as a time-varying covariate. So this is time-invariant. Those are, cleverly, time-varying covariate. So it's a covariate or a predictor that we have in our model, but the numerical value itself can change over time. And this can be any of a large number of things: self-esteem, environmental stress, depression, whatever it might be. To think about this a little bit more before we move to the how we would fit this in the model, let's do kind of a thought experiment. Is in an earlier video when I was just talking about what is growth curve modeling, is remember remember if you happen to see it, is I talked about we can have an individual trajectory. So this is mine, all right? So I equals Patrick, that's me. All right, so I'm 6 years old, and you go in and you talk to my mom and you interview her about how many aggressive behaviors I've had, how many delinquent behaviors I've had, and you start when I'm 6 years old, and maybe I was here, and then I'm not gonna try to line them up, it just goes around here in this way, and we fit the best line that we could, the line of best fit. So I have an alpha sub Patrick, right? That's my intercept, and I have a beta sub Patrick, all right? And that's my slope. Now, in the typical either unconditional model, where we don't have any predictors at all, or the conditional model that has time-invariant covariates, that is like biological sex or something like that, these residuals that exist around the line, they're a really important part of the model. All right, they go very, very much so go into the estimation. We have residual variance at each time point when we pool over all individuals, but we primarily treat these as unexplained variance. It's just noise. Maybe it's true variability that's not explained by the model. Maybe it's random measurement error. All of these things are mixed into this residual. All right, and so I have an intercept and a slope. You have an intercept and a slope. Everybody in the sample has an intercept and a slope. In the time-invariant covariate model, then we conceptually gather all of those together and we say, well, on average, are there differences in the intercept as a function of biological sex? Are there differences in the slope as a function of biological sex? In the time-varying covariate model, we're going to take a step back and say, all right, this is the line of best fit for my trajectory. I'm a little higher, a little lower, higher, lower, higher, lower. But instead of just saying that these residuals are just kind of random variability around the line, it's just kind of humming around the line, and it's just unexplained variance, is that part of this residual might be due to something that occurred at that time point, or maybe the prior time point, but for now we'll just focus on a contemporaneous effect. So that is, let's say that instead of this entire residual being due to random variability, that part of it is random variability, all right? So this is just conceptual, we don't really do this in the model, but part of it is random variability, but part is due to some, I'm gonna say TVC, some time-varying covariate. Remember, this is antisocial behavior, so higher is bad behavior. At that time point, maybe I had a bad teacher at school. I had a teacher that was poor in discipline at school, and it poked up my residual, my time-specific measure, a little bit above what we would expect it to have been based on the trajectory alone. At this particular time point, maybe I had a good teacher. It's good at classroom management. It poked it down a little bit. And so you can see that we can have this system where we have higher, lower in the residuals, but we may have these time-varying influences that are pushing up, pulling down, pushing up, pulling down the observations around this line. So now part of the residual variability is due to random variation, but part of it is potentially explicable. And this opens up a huge number of kinds of hypotheses that we can evaluate. If we're looking at trajectories of antisocial behavior, we could look at peer group influences. We could look at family kind of predictors. Is my time-specific value of antisocial behavior at this time point elevated because I was affiliating with a deviant peer group in that year, but the following year I got involved in an honors program at school, something like that, and it pulled it down. If we're studying, say, substance use in adolescence, what is the role of environmental stress in the home or depression in the individual? We can look at any outcome. We can start to think about, well, there may be these person-level predictors that govern the trajectory itself, the starting point and the rate of change, but there are also these time-specific pokes and pulls and prods and pushes that also push those repeated measures around the trajectory. So how would that look in a growth model? Well, it's actually pretty close to what you would think it would if you just tried to picture it in your own mind's eye, right? So let's say, again, that we have antisocial at age 6, antisocial at age 7, 8, 9, 10, if that fits on. It has a residual. All right, here, here, and here. All right, so we have antisocial behavior from age 6 to age 10. We have some intercept and slope. So eta 1 is an intercept. We have eta 2 is a slope. All right, we allow those to covary. These go out to all measures at 1, right? That's what defines the intercept. Let's say that this is a linear trajectory. And so we have 1, 2, 3, and 4. And so now you can start to see the pieces coming together. This is an unconditional model. This implies some starting point, linear rate of change, potentially individual variability in starting point and rate of change. In a prior video, I brought in time-invariant covariates, where they were predictors of the growth factors. But now what we want to do is to bring in the time varying. And let's say that we're, looking at this antisocial behavior. Let's say that we also in our data set have a child's report of perceived stress at age 6 and 7 and 8 and 9 and 10. All right, now this is not a time-invariant covariate because perceived stress changes over time. Now we're going to allow these to covary with one another, and I'm just going to do a kind of a sloppy way of doing this is all of these covary with one another and the growth factors. That's a standard modeling is all exogenous covariates correlate with all other exogenous covariates. But look at what we can do. Now again, I'm drawing this as a path diagram and a structural equation model. This all holds equally within the multi-level model. Is what we do is in the time-invariant covariates, we brought those into the level 2 equations. In the time-varying covariates, we're going to bring those into the level 1 equations. But they're all numerically isomorphic. They're the same models that we're discussing so far. So what we can do is say, all right, remember a one-headed arrow represents a regression coefficient. So we are going to use environmental stress in the home. So we just ask the kid, in the last 30 days, how much did your parents argue? How much did you know that about money problems? Whatever it might be, whatever developmentally appropriate measure of stress that you have. And notice what we're doing. When we have the time-invariant covariates, we're saying, is there a shift in the intercept or the slope of the growth trajectory as a function of changes in the covariate? Here, we're saying the same thing, right? That there's a 1 unit change in the predictor, all right? And just we call these gammas, let's call these kappas, all right? Just to differentiate, that's just a regression coefficient. Doesn't matter what we call them, I'm just gonna call them kappa to keep track of them. A 1 unit change in stress at age 6 is associated with a kappa unit change in antisocial behavior at age 6. But here's the cool part, is that is above and beyond the effects of the underlying growth trajectory. That is, it's trying to poke or pull that repeated measure, that residual around the trajectory. So these are time-varying influences on antisocial behavior net the underlying trajectory process. So when we think about building a model that reproduces the means, the variances, and the covariances of our dependent variables that we observed, when we don't have the time-varying covariates, we have to reproduce the mean and covariance matrix solely as a function of the growth factors. Here we're bringing them in and saying, well, we're going to reproduce the mean vector and the covariance matrix of our repeated measures as a joint function of this individual specific trajectory that are captured in the growth factors and the individual and time specific influences at the level of the TVC, the time varying covariate. That's those little pokes around the trajectory as it's unfolding. Now, once we start thinking about this, and it's very cool in how these models work, we can start to see a whole number of things that we can do. So for example, we could impose an equality constraint to test a model where all the TVCs are allowed to free, the coefficients, restrict it where they're all set to be equal. And what that does is gives us a formal test as to whether the strength of the time-varying covariate changes with age or with development. So for example, the environmental stress, the impact on antisocial behavior may get stronger as the child becomes older. The child becomes more cognizant of the environment, starts to understand more when the parents are arguing or if there are money problems. And so that's a testable hypothesis. Another cool one is, notice how I've drawn it is a contemporaneous effect. So stress at age 6 and predicting antisocial at age 7. Well, it's easy to lag this as well. So what we can do is have stress at age 6 predicting antisocial at age 7, 7 to 8, 8 to 9, 9 to 10. And so that too becomes a testable hypothesis. Does earlier stress predict later antisocial behavior above and beyond stress at that same time point? You can start to see the similarities of the autoregressive model that we talked about in an earlier video. Does stress at age 6 predict antisocial behavior at age 7 above and beyond the effects of stress at age 7? But the big difference with the autoregressive model is we're modeling the stability of antisocial, that time-ordered relation of the repeated measures, as a function of these latent growth factors. So we can lag those as well. Another extension that we can do is we could expand it to have covariates that are time invariant. All right, and so these we can have here and here, and we change the covariance structure a little bit. Again, this is standard that we would do, and we'd covary the disturbances now of the latent factors, just as we did with the earlier TIC model. But now you can see that we're building this really interesting model of individual variability in these developmental trajectories over time. Those trajectories are in part governed by information about our time-invariant covariates. So we might have biological sex and cognitive stimulation was the example I used in the prior video. But at the same time, we can incorporate these time-varying covariates, that the time-invariant covariates are governing the trajectories themselves. The time-varying covariates are contributing to the residuals around the trajectory. So you get this kind of person-based prediction here, and this person-time-based prediction here. And then we don't have time to talk about it here. The models start getting a little bit more complicated, but just as we set equality constraints here, we could, for example, interact the covariates with the time-varying covariates, and to say, does the strength of the relation between the time-varying covariate and the outcome vary for, say, boys versus girls? It may be that girls are more impacted by environmental stress in the home, especially as they get older. All of these are very straightforward tests that we can do in this model. So this is a fully time-invariant, time-varying covariate model. Again, I've drawn it as an SEM. We can do exactly this model within the multi-level framework. And there's one limitation though. And the limitation of this is, notice, although we've put this really beautiful growth process on the repeated assessments of antisocial, we have a starting point, we have a rate of change, maybe we have a piecewise linear, maybe we have a curvilinear, something like that. We have this growth process on antisocial. We don't have any growth process on the time-varying covariate. That is, each value, each variable takes on a mean and a variance and a covariance, but we're not structuring those in any way. In other words, we're not fitting a growth model to the time-varying covariate. We have a growth model for the dependent variable, but not for the time-varying covariate. In a lot of applications, that's fine. We wouldn't expect systematic growth on the time-varying covariate. But there are a lot of situations where we might believe that the TVC itself is governed in part by a growth process. And what we'd like to do is to take this time-varying covariate model and build an intercept and slope for the TVC as well. And that's called a multivariate latent curve model, and I'll explore that a bit in a later video. And it would expand in pretty much the way you would think it would. Is what we're going to do is lose the time-varying covariate effects and build an intercept and slope for the TVC, and then work on building a model where we have two growth processes at once. So that, in a nutshell, is the time-varying covariate model. I think it's really exciting because it not only introduces these factors that govern the starting point and the rate of change of what you're studying, but once those trajectories are unfolding, we can build a very rigorous model of time-specific influences that are capturing these time-to-time pushes or prods or pulls that govern the repeated measures over time. So as always, I hope this has been of some use, and thank you for your time.